Okay, so this is going to be another video just talking about some basics of optics, not just Snell's law problems, but looking at some just general conceptual stuff, and also the concept of total internal reflection. So looking at this worksheet here, it says the ray diagram below shows light reflecting from a mirrored surface. Label the following items: incident ray, reflected ray, interface, normal, angle of incidence, and angle of reflection. So just really quick, I'm going to sketch this on my sheet. I've got the normal, here's the incident ray, and let's see, label the following. Incident ray. Incident means incoming. Incident means incoming. So when you see incident angle or incident ray, that's the incoming ray. Reflected ray, you can see that here because here's the interface. I'll get to that in a second. So this is incident ray. Here's the reflected ray. Interface. This is the interface. This is the boundary either between two mediums, or it could be a solid boundary like a mirror. So this horizontal line here, that's the, I don't know what I'm writing. That is the interface. That horizontal straight line. Normal is this dotted line. It's drawn at 90-degree angles to the interface, and you always measure angles from the normal when you're dealing with optics and stuff. Angle of incidence and angle of reflection. Angle of incidence and angle of reflection, and you should remember, hopefully, that for reflection the angle of incidence is equal to the angle of reflection. Now it's more complicated when you have a refraction going from one medium to another. This is a very simple relationship for reflection. So those are just a couple basic stuff. Use a protractor, we're not going to do that. Do the rays in this diagram obey the laws of reflection? Hard to tell without actually measuring. What we would do is get a protractor, put it there, and make sure that the angle of incidence is in fact equal to the angle of reflection, and if that's true, then everything is fine with the law of reflection. I'm going to skip this. This is not something that applies to us. Going on to total internal reflection and the concept of the critical angle. Let me clear this out. So it says in the previous problem, light rays were bent away from the normal when traveling from an optically dense medium. Optically dense material. Remember, optically dense just means it has a bigger refractive index. Into a less optically dense material. This is another way of saying that the incident ray was traveling slower than the transmitted ray. If the incident ray hit the inner surface of the diamond at a larger angle of incidence, the transmitted ray would bend 90 degrees away from the normal, so that it was just grazing the surface of the interface. The angle at which this happens is called the critical angle. So you see the image here. At some point, if you're traveling from a medium that has a high index of refraction into a medium that has a lower index of refraction, if you increase the angle of incidence, at some point you see this refracted ray is going to approach a 90-degree angle with the normal. And if you increase past that angle, you see we don't have any refraction anymore. We only have reflection. At this point, this is called total internal reflection. And this minimum angle right here, right at this angle here, this angle of incidence where it just barely starts to occur, that's called the critical angle. So going back to the question, it says use Snell's law to calculate the critical angle for diamond. So we know that when we're talking about critical angle, the critical angle, the angle of refraction is exactly 90 degrees, because that's the angle of incidence at which the angle of refraction is 90 degrees, and past that angle you don't get refraction anymore, you only get reflection. So we have n1 sine theta 1, and remember this is, I'm going to go ahead and say this is theta c, the critical angle. At the critical angle, we know theta 2 is 90 degrees, and you should recall hopefully that sine 90 degrees is 1. So I can simplify this. I can say sine of the critical angle is n2 divided by n1, and so the critical angle is equal to the inverse sine of n2 over n1. So if I find that for this problem, n2 is 2.45, and 1 is 1. Can't even type it in correctly. 2.45, and I'm doing the inverse sine of basically of 2.45. So inverse sine. Of course, in the problem, I'm being silly now because I almost forgot for a second. This is the diamond right here, so this n1 is what should be 2.45. Almost messed up my calculation there. I should be putting an inverse sine of 1 divided by 2.45, and that's going to give me an angle of, let's see, divide by 2.45, inverse sine 24 degrees. So the critical angle is 24 degrees. If you go past that, you have total internal reflection. If you go below that, you still have some refraction going on. So that's how you would calculate the critical angle in a simple situation. The next question says, it does not make sense for the angle of refraction theta 2 to be greater than 90 degrees. Explain why. Because if the angle of refraction were bigger than 90 degrees, looking at the simulation, so here is right at 90 degrees between the normal and the refracted ray. Past 90 degrees would basically mean your refracted ray, quote unquote, would be on this side of the interface, which is not possible because then you're talking reflection, not refraction. So it's not possible to have an angle of refraction bigger than 90 degrees. And just one more question. You can read what it says up here. This question says, can total internal reflection occur if a light ray traveling through the air hits a block of plexiglass? Why or why not? No, because you can only get this phenomenon, total internal reflection, when going from a higher to a lower index of refraction. It's not possible to get total internal reflection going from air into anything, because pretty much everything has a higher refractive index than air, which has a refractive index of 1. So hopefully that helps you understand a little more about critical angle. Good luck.